Okay, so now we're looking at the approach of identifying trigonometric functions using the unit circle. And so we were looking at before, and actually I do want to come back to this, but we were looking at before the ratio of sides of a triangle from an angle. So this one has some space in here. We also talked about last week about the angle and the ratio of sides. If you had similar triangles, it didn't really matter which similar triangle you used, you would get the same result. And that's why we can limit things down as the unit circle. So we had talked about, again, another thing we had just kind of review. Let's say you had some point, and I called it XY. But in this case, your book calls it AB. So let's say you have a point at AB. So if you located that point AB, and so you graphed it, and so it doesn't matter, but let's just say that right here is your point AB. And we looked at the ray starting at the origin, the point starting at the origin, going through that point. And from there, we were able to make a triangle. And it's a right triangle. And that angle theta was the angle that was attached to the terminal side of that ray and the x-axis. And it was the closest part of the x-axis. So sometimes it was the negative part of the x-axis, sometimes it's the positive part of the x-axis. And so this was our angle that we were looking at. And so this side here, this length in here, that is a length of B. It's the height, which notice is our y value of our point. And A is the x value of our point. And that base down here is length A. And so from here, we could use our trigonometric functions to find the ratio of our sides. Well, actually, we had to do one other thing, right? We had to figure out what this hypotenuse was. And they called it R. Think of it as a radius of the circle. And so by Pythagorean theorem, we knew that R squared is equal to A squared plus B squared. Or R is equal to the square root of A squared plus B squared. I just want to make a quick comment here, because a lot of times students think that this is the same thing as A plus B, but that is not true. I can't take the square root of a sum and break it down as the square root of each piece and then sum it. It's not equivalent. Okay, well, let's say we take this triangle and let's limit it, or let's expand it. It depends on if R is bigger than or smaller than 1. But we saw that if we took and we made triangles either bigger or smaller, so for instance, I could come out here, right? That angle theta is the same for both triangles. They're both right triangles. This angle in here has to be the same. And so that we knew then the trigonometric functions at those angles, those ratios were going to be equivalent. And so that's why we can limit our radius or make our radius be 1. So we're going to use the unit circle. This is where x squared plus y squared is equal to 1. This is a circle centered at the origin with a radius of 1. And so from here we could Let me get some more space. So let's look at our trigonometric functions. And so here, if we had some point, and this now is 1, this is at some point, let's say a, I don't know, a sub 1, b sub 1. Then our trigonometric functions, sine, let's make this theta, of theta. So this is equal to the opposite which is our length of y, which is b for that point, and a is our adjacent side for this point. And we know that the hypotenuse was 1. So sine theta, which is our opposite, which is b, all over our hypotenuse, which is 1. So b over 1, or b. So this makes it a lot easier because basically now our sine and our cosine values at that angle are either the x or the y value of that point. And so cosine theta, this is the adjacent side, which is a, all over 1, or a. Tangent theta, opposite over adjacent, well, opposite is b, all over adjacent a. And then we can get the other ones by the reciprocal. So the reciprocal function of sine theta, that one is cosecant theta. So this would be 1 over b. The reciprocal function of cosine theta is secant theta. That would be 1 over a. And cotangent theta is a over b. Oops. And these all should be subs of 1 in this case. Unless we want to just get rid of that sub 1 in here. That might be easier. There we go. Okay.
So, question real quick. Are you saying that when it is a circle like that, we would assume that the hypotenuse is going to be 1?
So if they're telling you that you're working with a unit circle, we can, or yeah, we know that that hypotenuse is always going to be 1.
Well, if it's a unit circle, it's going to be 1.
Yes.
Okay.
And so in this section, everything is, we're going to assume, let me just see if they say it. Yeah, it says the point P on the unit circle that corresponds to the real number T is given. Find sine of T, cosine T, yada, yada. So for example, so you had some homework like this, and so it was given us a point. And so let's say you have the point negative square root of 3 all over 2, comma, negative 1/2. So again, so this point is on the unit circle, and it corresponds to the real value T. And we want to find cosine T, sine T, tangent T.
Professor, what is T?
So T is basically, instead of calling it theta, we're going to call it T right now.
Oh, okay, okay.
And so T, we're going to, so T is just the angle measure that we're using. So first step I would do on all these is I would graph this. And so I would plot this. I would figure out what quadrant I'm in. And so if we plot this, I have negative root 3 over 2. And so I would just come over on the x-axis and I would just put negative 3 all over 2. And then my y value is negative 1/2. So I know my point is contained in the third quadrant. And this is 1. So basically, we just have to look at the x and y value of our points. So cosine of t, this is equal to x over 1. And our x value is negative root 3 all over 2. Sine of t, and this is actually equal to our y value. So this is negative 1/2 all over 1. I tend not to, they tend to leave it with, and this might be just easier for you guys, they tend to leave those points with the signs. When I think of it as triangles though, I don't like to think of that as the lengths as negative. And that's where I go back and think to myself, is cosine or sine positive or negative in quadrant 3? Tangent of t, this is equal to y over x. So my y value of my point is negative 1/2. And my x value of my point is negative root 3 all over 2. So think of this as division of two fractions. So take the fraction in the numerator times the reciprocal of the fraction in the denominator. So reciprocal is flipping it, that would give me negative 2 over root 3. So I notice my 2's cancel in the numerator and denominator. Negative times negative is positive. And so I have 1 over root 3. And we don't like radicals in the denominator, so multiplying this by root 3 over root 3 would get rid of that problem. And so this would be positive root 3 over 3. So the next example in the book pretty much does the same thing, but this time they tell you basically that you're not on the unit circle. So you're going to have to figure out what R is. And that's similar to what you had done in that last homework. They kind of phrase this a little differently than I would, but they say use the fact. So let's look at this example. So use the fact that a trigonometric functions are periodic to find the exact value of each expression. So use the fact that trigonometric functions are periodic to find the exact value. Okay, so we really haven't talked about it being periodic. You know what that's talking about? Trigonometric functions are periodic.
Professor, I had a quick question before we did this example. Regarding the unit circle, and you put negative square root of 3 over 2 and 1/2 on the point of the 180 degrees. but on the unit circle, it represents 150 degrees.
Are you talking about from a different day?
Oh no, sorry, I messed that up. I didn't see the negative on the 1/2 down there below the graph. And that
Okay.
negative, yeah, I was just kind of confused on how you got negative square root of 3 over 2. Just as that place, is that just how it is on the unit circle then? Or is there a way to get that?
So from the point, if it gives you the point, then we would do it this way. And you would graph the point. And we'll see that there's kind of multiple ways to do this. But right now we can use the fact that basically I tend to like to say that this is actually sine of b is actually equal to just y, the y value of your point. This is just equal to the x value of the point. This is equal to y divided by x if we're on the unit circle. So cosecant's 1 over y, secant is 1 over x on the unit circle, and then cotangent is x over y. So basically, knowing that value, knowing that fact, we can say right away that cosine of theta for this point is going to have to be the x value, which is negative root 3 over 2.
Okay, can you scroll back up a little bit so I can get a little snip of that unit circle? Yeah, the x squared, yeah, right there. Thank you. All right.
And so you were right when you were talking about angles though, and reference angles. We didn't even talk about what angle would have gotten us down there to give us those x and y values on that unit circle. And we'll look at that in a little bit. Use the fact that it's periodic. What do we know about, anybody know anything about periodic functions or what that even means?
Does that mean like every X amount of degrees?
So basically it's going to start repeating itself. And you're right, every X amount of degrees or X amount of radians. And so this is the shortest distance. It takes the function to start repeating itself. And so we talked about cofunctions, or actually, well, we did, but we also talked about coterminal angles. And so we talked about there were an infinite number of angles that could get us back to the same spot. Well, that would give us the same trigonometric value, right? And so basically all of our trig functions are periodic. We have to be careful though how close they are. So all the trig functions, cosine, sine, except for cotangent and tangent. So secant t and cosecant t. These are periodic. Every 360 degrees. Well, we talked about that being 360 degrees times k would get us to another value of the integer. Or if I put this in terms of radians, 2 pi. Tangent is a little different than cotangent. Tangent t and cotangent t. We'll look at this in a little bit later, probably this week. The period is 180 degrees, or just pi. So if we were looking at the fact in that example saying using the fact that it's periodic, and we wanted to look at tangent of 405 degrees. So it's periodic. I shouldn't have pasted this thing in here. Every pi it says, or 180 degrees. So I would look at my 405 degrees. And so basically that is one full circle, 360 degrees. I would do this different. Plus 360 plus 45. So this is right here. So this is 405 degrees. So this is equivalent to, I have to figure out basically what I'm multiplying 180 by. Let's look at that. So let's look at 405 minus 180. Let's see how many times we have to do this. So 5, let me borrow, that's 2. So that gives me 325. So minus another 180, right? Well, I knew that was going to happen because twice. 5.
So you get 225.
225, thank you. 3 minus 1 is 2. I was just seeing that. 2 minus 1, so 145. Oops. Sorry, and I borrowed, so that's just 45, which I knew I would get. So basically, we can rewrite tangent of 405 degrees is the same thing as 45 degrees plus 180 times 2. That's how they're representing it. I really don't like doing it this way. This is equal to tangent of basically 45 degrees. To me, just drawing the angle and finding the reference angle is a lot easier than me thinking about it being periodic and subtracting off 180 or pi each time to get to this. And so this is the same thing. They're saying because it's periodic, it has to equal tangent of 45. And then tangent of 45 is 1. And I'm in quadrant 1, and I know it's positive. So when they're asking you to do this, I'm okay with you doing it how we were doing it at the end of last week. So if it said, look at cosine of 37 pi 6. Okay, so I see that 6 goes into 37 approximately 6 times, right? 6 times 6 is 36. So this is about 6 pi, or let me break this down. Right, it goes in there 6 and 1/6. So remember, this is the same thing as addition. And so we can think of this 37 pi over 6. This is the same thing as 6 pi plus 1 pi 6. And so no, you can check it. Common denominators, this is 36 pi 6 plus pi 6 is 37 pi 6. Well, let's break down 6 pi, right? 6 pi is periodic, and this is just looping around 3 times. So this is 3 full revolutions plus some pi 6. And so now I can say that cosine of 37 pi 6 is the same thing as cosine of pi 6. And so cosine of pi 6, if you don't remember that one, 6 goes into 180 30 times. So cosine is 0, 30 degrees. So there's 3 fingers above, so that one's the root 3 over 2. And I'm good because I'm in the first quadrant. Let's really quick, one more thing before we get it into the unit circle. Let's talk about even and odd functions.
Professor?
Mm-hmm.
So like on the homework, I think 7.3. So like it's actually a negative. So it's like negative pi over 4. And it says like find the reference angle. So I was confused, like how would you having a negative sign. One of the tutors told me that you're supposed to like add 360 until you get a positive number.
So if you want the reference angle of negative pi fourths,
It was negative 5 pi over 4.
Oh, negative 5 pi over 4. I always tend to graph it. I notice that this goes in there one time, so I'm going to be about a negative pi. So I know negative pi is clockwise, so I'm going to start and go clockwise direction. So this is the same thing as negative pi minus pi fourths, because there's one left over. And so pi fourths I know is 45 degrees, so I know I have to go about 45 degrees. Oops, this direction. So reference angle is always this angle between this terminal side and the x-axis, that's closest piece. And so in here, this angle between this terminal side and the x-axis is a length of pi fourths. So if we had let's see what happens when we do this, when what the tutor said. If we had added 360 or 2 pi here, well, basically and she's right, or he's right, 2 pi, right, is a full rotation this way. But if we subtracted off what they just had, negative 5 pi fourths, this piece, that would get us right here. So you could think about it, and that could help us. It's just going to be, the problem is that wouldn't have given you the reference angle. That would have given you this angle right here, right? And so that wouldn't have exactly given us the reference angle. Right, so if I got a common denominator, which is 4, this would be negative 5 pi fourths plus 8 pi fourths. This gives me 3 pi fourths. So 3 pi fourths is called a coterminal angle because this gives me the same terminal side as this one. But if I graph the angle of 3 pi fourths, that is from here to here. And notice that's not my reference angle. So the reference angle is always an angle between 0 and 90 degrees, or 0 and pi halves, between the terminal side and either the positive or x-axis, depending on what quadrant you're lying in.
Where did you get 8 pi from, Professor?
The 8 pi, I was, the student's question was, can I just add 2 pi to it, or 360 depending on degrees? And so in order to add 2 pi to my negative 5 pi fourths, I need it to be a fraction. I need common denominator. So I just multiply my 2 pi by 4/4 to get a common denominator. And so 4 times 2 is 8. That's where this 8 pi is coming from.
Do you think you can do it? Because I get confused while doing it with fractions. I converted it to degrees. I know it's more work.
You're right. So it is a little more work to do it and convert it to degrees first and then go back. I think that though, once you keep on doing that, you're going to notice and start noticing the pattern. You know, pi fourths is 45 degrees, pi thirds is 60 degrees, stuff like that. And then when you look, and when we look at the unit circle, that will help too.
So like
So
if
now,
so like if you were to do it to degrees, so it's like negative 5 pi over 4 and then times 180 over pi.
exactly.
And then I got negative 22. And then I added 360.
Something's wrong. I think something's wrong there. So let me just make some more room on my page real quick. Maybe. Sorry, my computer's slowing down. So you're right, to convert it to degrees, so I'm going to take my negative 5 pi fourths, and you were right to say multiply it by 180 over pi. Your pi's are going to cancel. You said 4 goes into 180, 45 degrees, but 5 times 45, I think you said you had 22, right? But something's off on that. 5 times 45. So that's 225. So this is negative 225 degrees. And so now if I think about it with degrees, okay, negative, so I have to go clockwise. This is negative 180. So I usually go to an X or Y axis. I know what degree is, and then think what I have to add to get up to this. So 180 plus 45 is 225, so I have to go 45 degrees in here. So this is negative 225 degrees. And then reference angle is always between terminal side, closest x-axis piece. And so this is 45 degrees. And so we would have to convert 45 degrees now back to radians since we started with radians. So pi times 180. Over 180. So 180 goes in, 45 goes into 180 4 times. So this is a pi fourths.
Yeah, I messed up on the negative 225. I added 360.
Yeah, and so that would get it, that would give you if it asked you for a coterminal angle, that would have given you the coterminal angle, but it wouldn't have given you the reference angle. You could have, when you added that 360 to that, that would have given you, like we had said, this angle right in here, which is not the reference angle because it's over over 90 degrees. So you had to use this piece.
You added the 45 angle.
I know this is 180 degrees. And so I know that 225 minus 180 degrees, this is 45 degrees.
Oh, okay. Well, yeah, because I forgot reference angle is less than 90 degrees.
Yeah.
Okay, thank you.
Yep. So even and odd functions. I can just do this real quick. Okay, so what does it mean to be an even function? It's an even function if the following holds. If f of, sorry, maybe I should write this. If f of negative x is equal to f of x. And it's an odd function if f of negative x is equal to negative of f of x. Just a little note if you don't remember, but even functions, these are symmetrical. Across the y-axis. And odd functions are symmetrical across the origin. Okay, so we can think of this as with theta. Let's use theta instead of x so we don't get confused. So let's look at cosine of negative theta. And let's say negative theta, or let's say positive theta is between 0 and 90 degrees. Well, negative theta, isn't that just telling you that you are going clockwise instead of counterclockwise? So let's say that this right here, it doesn't matter, it's just as long as it's between 0 and 90 degrees. Let's say that this is negative theta. Well, that would mean then if I took that same angle and I put it above the x-axis, this would be positive theta. So let's say we had some point on here. So here, right here, let's say that this is a point AB. So if I went down and I folded my paper along that x-axis, right here, this point is negative A, negative B. I'm sorry, it's not negative A, it's still A, right? But negative B. remember cosine is the x value. So notice that cosine of negative theta, this is equal to a. And cosine of positive theta is equal to a. So we can say then that cosine of negative theta is equal to cosine of positive theta. And cosine is a even function. So same kind of idea, we can do that with sine.
Wait, Professor.
Yeah,
So the function is even if the negative is inside the parentheses?
it's even if you plugged in a negative value, it would give you the same thing as if you had plugged in the positive of that value. So
Okay.
if I had plugged in
So
negative
both
of
of them
an
should
angle
work?
theta, I would get back the same thing as a positive.
Okay.
But odd, notice sine is in terms of y, the y value of your point. Sorry. And so if I look at my y value of my point, so let's look at sine is your y value. So sine of positive theta, assuming that we're on the unit circle, is your b value. But sine of negative theta it's negative b. So notice if I multiply this equation, both sides, by -1. So if I do that, I get negative sine of theta equals negative b. Well, that's the same thing as sine of negative theta. So we can say that negative sine of theta is equal to sine of negative theta. So sine is a odd function. So just the fact of knowing this, it just makes it a little easier, because if you're given a negative angle, or you can either say it's the same thing as the trigonometric function at that positive angle, or pull the negative out front, depending on if it was even or odd. And since all the other trig functions are terms of cosine and sine, then we can determine if they're odd or even. Okay. So questions on that? I'm kind of reading your comments.
Okay, Professor, I was writing down as you were just explaining why this is an odd function.
Mm-hmm.
So can you please repeat it?
Yes. I know sometimes it's hard to, you guys are trying to keep up with the writing and you're not processing what I'm actually saying. So In the beginning of class, when we were looking at the unit circle, and we said we could limit things down so that our radius is 1, and because of that, we can say that our trigonometric functions at that angle really depends on the x or y value of our point. And so cosine ended up being the x value of our point, and sine ended up being the y value.
Okay.
And so if it told me to look at cosine of negative theta, well, remember negative theta, that just tells me that I'm going clockwise instead of counterclockwise.
Okay.
So I just started at our initial standard position, and I went negative theta degrees. And I just defined it that right now we were just going to have theta between 0 and 90 degrees. So I could help
Okay.
you.
Okay.
Well, if I went positive theta, it's the same measure, right? But it's just saying to go in the opposite direction.
Direction, yeah.
And so if I looked at the point on here, my x values are going to stay the same, but my y value are changing signs depending on if I had negative theta or positive theta.
Okay, thank you.
Then you got that then? So
Yeah.
basically, that's how we can
I
derive
get
it.
that part.
Any other questions? So based off this, if we know that tangent theta is, if we rewrote it in terms of sine and cosine, remember tangent theta could be written as sine theta over cosine theta. So tangent of negative theta, this is equal to sine of negative theta all over cosine of negative theta. Well, sine of negative theta up here, we already said that that's the same thing as negative sine theta. We just proved it. And cosine of negative theta, we said that's the same thing as just positive cosine theta. So if I pull my negative out front, which I can, this is negative sine of theta over cosine theta. Well, that's negative tangent theta. So that tells me then that tangent is an odd function. So tangent theta is odd. That's saying that tangent of negative, if I have tangent of a negative angle, this is equal to negative tangent of that positive angle. So same sort of reasoning, I can say that cotangent theta is odd. That's just cosine over sine. And then secant theta, that's 1 over cosine, so this is even. And cosecant theta, that's 1 over sine, so this is an odd. Maybe not equals, or is instead. So basically, if we know, again, one angle, then we know another one. We know the negative of it. And that's where the unit circle could be really helpful. Okay, so before we jump into the unit circle, I think we should take a break. Okay, so here's the unit circle, and we're going to fill this out. And this is a helpful tool to help you with hopefully memorizing these specific angles. And so let's look at the following, and we're looking at the following points. And so here we have a point at 0, 0. Okay, so if we look at this in degrees, well, for a standard position, we can think of this as we haven't even moved or rotated anything. And so this would be 0 degrees here. And for, if we made one full rotation and got back at the same place, this would also be 360 degrees. And so now thinking about this, let's actually go around in degrees and then we'll go back and we'll put in our radians. And so if we rotate, you need to know the next one, which is 30 degrees. Here is 45 degrees, 60 degrees. So the y-axis, this is 90 degrees. And then, okay, so to get to this, basically our reference angle is 60 degrees. So if you think of 180 right here, minus 60, that is 120 degrees. So 120 degrees. 180 minus 45 degrees, because our reference angle is 45 here. That is 135 degrees. A reference angle of 30 degrees here, if you want to think of it. So 180 minus 30, that's 150 degrees. So full line, to get to a full line, that's 180 degrees. So let's think of this again as reference angles. And so reference angles from our negative x-axis going into our third quadrant. So if we add 30 degrees to 180, that's 210. So 210 degrees here. 180, if we added 45, another reference angle, that's 225 degrees. Oops, wrong spot. And then 180 plus 60, that's 240 degrees. And then if we went to our negative y-axis, so rotation from standard position, that's 270 degrees. So thinking of our reference angles, so our reference angles from our fourth quadrant are going to be with a positive x-axis. Did that just erase where I wanted it to? Yeah. Sorry. We have 360, and if we subtract 30 degrees, or 30 degrees right here, that would give me 330. Maybe I should have gone from, this is 360 degrees for a full rotation, and if I subtract 45 degrees from 360, this is 315 degrees. And then 360 minus 60 degrees to get my other reference angle, that's 300 degrees. And so now we should be able to have the radian measures of all of those degrees. Let's do a different color. So this could either be 0 radians, or a full rotation is 2 pi. So 30 degrees, multiply that by pi over 180. Well, 30 goes into 180 6 times, so this is pi 6. 45 degrees, this is pi fourths. 60 degrees, this is pi thirds. 90 degrees, this is pi halves. And so to get the other ones, we can kind of do the same sort of idea, thinking of it as reference angles. So a full rotation, or not a full rotation, but a half a rotation of a circle, that's pi. Well, let's think of our reference angles from pi. We were either going to subtract pi thirds, pi fourths, or pi 6. all of those to get to these specific angles. So if we looked at pi down here minus pi thirds, well, I need to think of this as a common denominator. So this is 3 pi thirds minus 1 pi thirds. That is 2 pi thirds. 2 pi thirds is with 120 degrees. So pi minus pi fourths. So common denominator, pi is the same thing as 4 pi fourths. So 4 pi fourths minus 1 pi fourths is 3 pi fourths. Pi minus pi 6. So 6 pi 6 minus 1 pi 6 is 5 pi 6. So do the same thing now, but now we're going to get to the third quadrant, we would use our reference angles of pi thirds, pi fourths, and pi 6, but we would add it to pi. So if I took pi plus pi thirds is actually, let's go to pi 6 first because that's the 30 degrees. So again, common denominator. So think of this as 6 pi 6 plus 1 pi 6. That gives me 7 pi 6. So 4 pi fourths plus 1 pi fourths is 5 pi fourths. And I can think of this as 3 pi thirds plus 1 pi thirds is 4 pi thirds. And then 270 degrees, this is 3 pi halves. So instead, now to get to the fourth quadrant, I need to use 2 pi. So I'm going to go over here and I'm going to rewrite this as 2 pi, and then I have to do my reference angles to get to them. So I'd have to either, in this case, I'd have to subtract it from 2 pi, or reference angles. But I'm going to need a common denominator in each one of these cases. So pi thirds, that's 60 degrees. So so to get a common denominator, I'm going to have to multiply this one by 3 over 3. So this is 6 pi thirds minus 1 pi thirds. 6 pi minus 1 pi is 5 pi. So this is me 5 pi thirds at the 300 degrees. So 2 pi, get a common denominator, multiply this by 4 over 4. So this is 8 pi fourths minus 1 pi fourths. This is 7 pi fourths. And then common denominator is 6. So this is 12 pi 6 minus 1 pi 6 is 11 pi 6. So I kind of did that with reference angles. So you could kind of see that you're either going to be adding or subtracting, depending on what quadrant you're trying to get from pi, or you're going to be subtracting from 2 pi to get down to this fourth quadrant. You could have been doing this though with knowing those degrees, multiplying everything by pi over 180 to convert it to radian measure. So from here, you need to know the points or the values of those trigonometric functions. And so let's go through and write out the quadrantal angles first, those points. And we're thinking of this on the unit circle. And so we already mentioned here at the standard position is 0, 0. At pi halves, that point, x is 0, y is 1. Actually, I am wrong on that point 0, 0, aren't I? If I'm looking at that point right there, my x value is 1, my y value is 0. And then at pi, or at 180 degrees, my x value is -1, my y value is 0. At 270 degrees, my x value is 0, my y value is -1. So I don't know if you guys remember, but at 30 degrees, the x value here is the √3/2. And the y value, or we can think of this as 30 degrees, cosine of 30 degrees is √3/2. Sine of 30 degrees is 1/2. 45 degrees, cosine of 45 degrees, it's our x value of our point, is √2/2. Sine of 45 degrees is √2/2. So 60 degrees, I can think of it, sine of 60 is 1/2. Sine of 60 is √3/2. Okay, so from here, all we have to do is think of a sign positive or negative in these quadrants. And this, they're basically reflections. This right here is reflection across here. And so my y value stays the same, √3/2, but my x value is now not positive anymore, it's negative. X is negative in quadrant 2. So my x value is just going to be the negative of my x values in my first quadrant, but my y values are going to stay the same here. And so 135 degrees is the same as 45 degrees for my y value, √2/2, but x is going to be negative √2/2. At 150 degrees, my x value is going to be negative √3/2, but my y value is positive 1/2. Third quadrant, we said cosine and sine are both negative. Basically, it's just the negative, and these are reference angles. So a reference angle, 30 degrees at 210 degrees, same thing as 30, but they're both negative. So this is going to be negative √3/2 and negative 1/2. So 225 degrees, it's like 45 degrees, but both of them are negative. So negative √2/2 and negative √2/2. 240 degrees, reference angle is 60 degrees, just negative, so negative 1/2 and negative √3/2. Fourth quadrant, we talked about sine is negative, but cosine is positive. Our y values are negative in quadrant 4, but our x values are positive. So if I'm going around clockwise at 300 degrees, that's a reference angle of 60 degrees. So x at 60 degrees is positive. So cosine of 60 degrees is 1/2. Sine of 60 degrees is √3/2, but we're in the fourth quadrant, so it's negative √3/2. 45 degrees, reference angle for 315. Cosine of 45 is √2/2. It's positive in quadrant 2, but sine of 45 degrees is negative √2/2 in quadrant 4. Reference angle 30 degrees, quadrant 4. Cosine of 30, so it's positive √3/2. And sine of 30 is 1/2, but quadrant 4, so we have negative 1/2. Okay, so hopefully you can see where it's important if you know your your quadrantal angles, and 30 degrees, 45 degrees, and 60 degrees. You should be able to figure out those other ones pretty easily. And you could have done it a little differently than how I was doing it, but you would still get the same thing. So questions on that? Let's see. Okay.
So I'm just trying to label like each color. So to find the ones, the 30, 45, 60, that's the sine and cosine, the finger thing, right?
Yeah, we can use the finger thing to determine what that is. And then how I kind of remember again is if I was to write the alphabet and these in order, I know cosine comes before sine. And so that's why it's the number on the top. Not why, but that's how I remember. And then the formula to do this was root n over 2. N equals fingers above theta. And for sine, it was the number of fingers below. So 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay, so let's look at a couple of examples, and then I'm going to go back and do a couple of word problems from 7.3. So let's say it says find sine of negative 9 pi fourths minus tangent of negative 9 pi fourths. Okay, so let's first rewrite this. Because we know that sine and tangent, we can rewrite it so that those are not negative angles and those are positive angles. So let's use the fact, but you didn't have to. We could keep them as negative angles and you should be fine. But we're going to use the fact that we just learned that sine of negative theta was an odd function is equal to negative sine of theta. And tangent of negative theta, it was also an odd function, so that was negative tangent of theta. So I'm going to basically pull the negative out in front. It's not really what you're doing, but that's basically what it's equal to. So this is equal to negative sine of 9 pi fourths. But a negative and a negative, so this is plus tangent of 9 pi fourths. So once I did that, I would figure out where 9 pi fourths is. So to kind of get an idea, I would look at, because my denominator is smaller than my numerator, 4 goes into 9 twice with 1 left over. So that tells me I'm going 2 pi plus a 1 pi, and a 2 pi plus a 1 pi. So 9 pi fourths, 2 pi is 1 full rotation plus pi fourths. So I know my reference angle. Is pi fourths. So I have negative, so this is equivalent to, and we're in the first quadrant, so it's the same. This is contained in quadrant 1. So if you have to convert it, pi fourths is 45 degrees. Sine of pi fourths, so 45 degrees, 0, 30, 45. So there's 2 fingers above and 2 fingers below. Sine is below. So this is root 2 over 2. Tangent, so plus, this is the same thing as, let me just write it, sine of pi fourths all over cosine of pi fourths. Actually, tangent of pi fourths is the easiest one. So that's root 2 over 2 divided by root 2 over 2, which is 1. So this is negative root 2 over 2 plus 1. I want to write that as a single fraction, so I need a common denominator, which is 2. Making the common denominator, though, putting it in exact form, I cannot combine negative root 2 and positive 2, so this is 2 minus root 2 all over 2. Okay, so here's an example where on a test, I wouldn't allow you to have a calculator on here, but you showing me certain things on what you're doing is helpful instead of just telling me, oh, well, I know sine of 9 pi fourths is root 2 over 2, and just doing it that way. I forgot to go over domain and range. Let me do some domain and range, and I promise tomorrow we're going to start with word problems. Let's start with cosine and sine. Well, if we think about it with a unit circle, and we said that cosine of theta was equal to x, and sine of theta was equal to y. What is the smallest and largest x values that we get back? So notice on this, we're hitting all x values from -1 to all x values of +1. And so our domain is -1 to 1. right? So if I chose an x value right here, it's hitting the graph. My range, same sort of idea. If I look at my y values, all y values that I get back from my points are between -1 and 1. Usually go smallest to largest. So -1 to 1. That is interval notation. Don't get that confused with a point. So another way to write this is 0 is less, I'm sorry, not 0. -1 is less than or equal to x, which is less than or equal to 1. Come on. And same thing, doesn't want to work anymore. There we go. Range -y. And -1 is less than or equal to y is less than or equal to 1. We have to be careful with tangent theta. Remember, this is sine theta over cosine theta. We can never have cosine theta can never equal 0. If so, tangent is undefined. And so that when tangent theta is equal to 0, well, let's think about it. It's our x value is 0 here and here on our y-axis. So if we think of it with angles, that's at 90 degrees, that's at 270 degrees, or that is at pi halves, 3 pi halves. So theta can't be any of those. So theta cannot equal, let's do it first in degrees. So 90 degrees plus 180 k. K equals an integer. Or theta cannot equal pi halves plus pi. Okay. If you think about it, we have to be careful with the other ones. Just see what they do. So this is for our domain of tangent, but our range you got to kind of think about fractions. And so you have to think about small numbers and big numbers in the numerator and denominator and what would happen. Because basically what we're going to be doing, our y value is, remember, our numerator for tangent, and cosine is the y value. So if we think about some number close to 1 but not 1 divided by a very, very small number. So if you have some number over a small number, and let's just look at it with 1 for a second, just to get the idea. That number on top is really changing. But let's say you had 1 over 0.1. That's actually equal to 10. If I had 1 over 0.01, this is equal to 100. So if I even get a number smaller to 0, 0.0001, this is equal to 10,000. So notice if I'm taking a numerator and I'm dividing by something that's getting smaller and smaller and smaller, getting closer and closer to 0, this number is blowing up. It's going to infinity. So I can do that same sort of reasoning with negative numbers, because our numbers are between 0 or -1 and 1. And so our range for tangent theta is actually all real numbers. Oops. And so we would do the same sort of reasoning with the other trigonometric functions. Those are all in terms of ratios of sines and cosines. And so we have to figure out when the denominator is equal to 0, you have to exclude those values. And then figure out what type of values you would get back when you plugged in values of theta that it was defined at. Okay. So that was 7.5. Let me take roll real quick. And I've been saying it pretty much for a week now. I will be covering 7.3 applications tomorrow, I promise.